The electron configuration of calcium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. You can double check you've got the right number of electrons by adding up all of these numbers. If you add these numbers up, you'll see it adds up to 20, which is the atomic number of calcium. It's an easy way to check you've got the answer right. The ionic equation to show how calcium reacts with water, you've got to include state symbols. So calcium is a solid, it's a metal. It's going to react with water, which is a liquid, and it's going to form ions. It's going to form calcium oxide, but as it's asking you to write it as an ionic equation, that means we need to have the calcium as an ion. It's going to be dissolved in water, so it's going to be AQ, plus hydroxide ions, which are also dissolved in water, so we're going to be AQ, plus hydrogen gas. Don't forget to make sure the equation is balanced, so we're going to need 2 waters and 2 hydroxide ions. The equation for the first ionisation energy of calcium, remember the definition. It's 1 mole of a substance in its gaseous state, and it's the enthalpy required to remove 1 mole of electrons to form 1 mole of singly positive ions in the gaseous state. So make sure you put those gas symbols there. As you go down group 2, the ionisation energy is going to decrease. This is because the ions are going to get bigger, so they have more energy shells, so there's going to be a weaker attraction of the electron. You could also say there's more shielding. Magnesium exists as 3 isotopes. In terms of subatomic particles, that's protons, neutrons and electrons, state the difference between the 3 isotopes of magnesium. So, magnesium 24 has 12 neutrons, magnesium 25 has 13 neutrons, and magnesium 26 has 14 neutrons. Or you could just say they have different numbers of neutrons. State how, if at all, the chemical properties of these isotopes differ, and give a reason for your answer. There is no difference at all. Chemical properties are determined only by the electron arrangement. It's not enough to say it has the same number of electrons. You've got to say it's either got the same electron arrangement or the same number of electrons in the outer shell. This one's a little bit trickier. We know that the AR is 24.3. We know one of the isotopes, which has a mass of 25, makes up 10%. We know there are 2 other isotopes, one that is 24, which we don't know the amount it makes up, so we're going to call that one Y. And we know there's one that's a mass of 26, And we know that plus y is going to make 90. So this would be 90 minus y. Okay, it's then just a case of seeing how good your algebra is, rearranging that and working out a value for y. So if y equals 80%, that means the isotope with a mass of 24 is going to have an abundance of 80%. We know that the two of them together added up to 90, so the abundance of the isotope with 26 must be 90 minus y, so that's 90 minus 80, which gives us an answer of 10%. In a time of flight mass spectrometer, each 25 magnesium ion is accelerated to a kinetic energy of 4.52 times 10 to the minus 16 joules, and the time of flight is 1.44 times 10 to the minus 5 seconds. Calculate the distance travelled in metres in the time of flight drift region, and it gives you Avogadro's constant. So we're going to be rearranging this equation to make sure we can work out distance. We have time given to us in the question, but we don't have velocity. So we're going to have to use the second equation to work out velocity. The one thing I'm not given is the mass of a single ion, so that's where I'm going to start. So I know that the mass of 1 mole of 25 magnesium ions, because it's only lost one electron and the electrons have a negligible mass, that's going to be 25 grams. Remember, the AR of any element is the mass of 1 mole in grams. We're working in kilograms in this question, so we need to be able to convert that into kilograms. So divide it by 1,000, and that gives you 0.025 kilograms. Now we've got the mass, we now need to work out the mass of 1 ion. We've got 1 mole of ions, so the mass of 1 ion is going to be the mass of 1 mole divided by Avogadro's number. Now we've got the mass of 1 ion, we can work out the velocity. So I'm going to rearrange the equation from the top to work out velocity. Now I've been given kinetic energy in the question, so I can put that straight in to the calculation. And I've just worked out the mass of 1 ion, so I can put that in as well. Now that was velocity squared, so I just want velocity on its own. So that's going to be the square root of the answer to the last bit. And that's velocity, so the units are going to be meters per second. Now we've worked out velocity, we can work out the distance. It's going to be velocity times time. We've just worked out the velocity, and the time is given to us in the question. And the units were meters per, velocity were meters per second, and time were per second, so that must leave the distance as meters. So the final answer is 2.13 meters. The concentration of an acid solution can be found by titrating the solution with a solution of alkali of known concentration. In such a titration, it was found that 19 centimetres cubed of 0.1 m sodium hydroxide were necessary to react with 25 centimetres cubed of a hydrochloric acid solution. So if we write down the information we've got underneath the equation, so we've got 19 centimetres cubed of sodium hydroxide, and we know it's a 0.1 mole of concentration. The hydrochloric acid, we know we've got 25 centimetres cubed. So it's the sodium hydroxide that we've got the most information about, so that's where we can start. And we can work out the moles of sodium hydroxide. Always make sure that when you do these calculations it is clear what you're working out each time. So we can do a vol times conc divided by 1000. So 19 times 0.1 divided by 1000 is equal to 1.9 times 10 to the minus 3. Now we can see from the equation that 1 mole of sodium hydroxide is going to react with 1 mole of hydrochloric acid, so it's a 1-to-1 relationship. So the moles of HCl are going to be the same as the moles of sodium hydroxide. Now we've got the moles of HCl and we've got the volume, we can work out the concentration. And we can do moles divided by volume times 1000. The moles are 1.9 times 10 to the minus 3. The volume in the question was 25. So that gives a concentration of 0.076 moles per decimetre cubed. Okay, if we approach this question in the same way, we've got 25 centimetres cubed of sodium hydroxide. We've got 0.1 solution concentration of sulfuric acid, and we know the volume of the acid is 22 centimetres cubed. So this is where I'm going to start. This is the moles I can work out. So again, make sure it's clear what it is you're working out. Now in this case, it's not 1-to-1, it's going to be a 1-to-2 ratio. So to work out the moles of sodium hydroxide, I need to multiply the moles of acid by 2. Now I've got the moles, I can work out the concentration. So the moles were 4.4 times 10 to the minus 3. The volume is in the question as 25, which gives me a concentration of 0.176 moles per decimetre cubed. In this question, 15.5 centimetres cubed of a 0.001 m solution of nitric acid, so let's put that underneath. React with 10 centimetres cubed of a calcium hydroxide solution. So we need to calculate the concentration of the calcium hydroxide solution. So I'm going to start with the nitric acid because that's the one I've got the most information about. So we're going to work out the moles of nitric acid. And that gives us 1.55 times 10 to the minus 5 moles. It's a 1-to-1 ratio. So the moles of calcium hydroxide are going to be the same as the moles of nitric acid. So then I can work out the concentration of calcium hydroxide by doing moles divided by volume times 1,000. The moles are 1.55 times 10 to the minus 5. The volume is in the question as 10, which gives me a concentration of 1.55 times 10 to the minus 3. It's a concentration, so it's moles per decimetre cubed. I now need to convert that concentration into grams per decimetre cubed. So the relationship between the two is moles per decimetre cubed equals grams per decimetre cubed divided by mR. It's a variation of moles equals mass over mR. And the mR for this one, if you calculate it, should come out at 74.1. If we multiply that by the concentration of moles per decimetre cubed, we end up with a concentration of 0.115 grams per decimetre cubed. This question breaks each step down for us. So the first thing we're going to do is work out the moles of sulfuric acid. So if we look in the question, we've got a volume and we've got a concentration for the sulfuric acid, so it's going to be 20 times 1 divided by 1,000, which is 0.02 moles. What is the number of moles of sodium hydroxide that must have been added to the acid? Well, it's a 1:2 ratio, so the moles of sodium hydroxide must be double the moles of acid, which is 0.04. What volume of 2 mole of sodium hydroxide contains 2 moles of sodium hydroxide? Well, by definition, we have got 2 moles per decimetre cubed. So we've got 2 moles in every 1 decimetre cubed, or we could say in every 1,000 centimetres cubed. So what volume contains 1 mole of sodium hydroxide? Well, if 1 decimetre contains 2 moles, then half a decimetre, or 500 centimetres cubed, will contain 1 mole. What volume of sodium hydroxide was needed to neutralise the sulfuric acid? Well, we've got the moles of sodium hydroxide, so the volume of sodium hydroxide is going to be moles divided by concentration times 1,000. And we know the moles are 0.04. From the question, the concentration was 2, which gives us a volume of 20 centimetres cubed. So we've got 10 centimetres cubed of a solution of sodium chloride, reacts with 15 centimetres cubed of a 0.02 molar solution of silver nitrate. What is the concentration of the sodium chloride in grams per decimetre cubed? So we're going to work it out in moles per decimetre cubed first and then convert it. But we will start with the silver nitrate because that's the one we've got the most information about. So that will allow us to calculate the moles. Now from the equation, the moles of sodium chloride are the same as the moles of silver nitrate. So we can say the moles of sodium chloride are equal to the moles of silver nitrate. We're then going to work out the concentration of the sodium chloride, which is going to be moles divided by volume times 1,000, which is 0.03. Then we want to change it into grams per decimetre cubed. So we simply times the concentration in moles per decimetre cubed by the MR, which in this case is 58.5. A solution of hydrochloric acid of volume 25 centimetres cubed, so we've got 25 centimetres cubed, was pipetted onto a piece of marble which is calcium carbonate. When all action had ceased, 1.3 grams of the marble had dissolved. Find the concentration of the acid. So we know we're starting with 1.3 grams of this. So neither appear initially to have enough information to work out the moles until you look a little bit more carefully. You've got a mass and you've got a formula, so there's nothing to stop you working out the moles of calcium carbonate. By using mass over MR. We know the mass is 1.3 and we can work out the MR. Okay, from the question the mole ratio is 1 to 2. So that means that the moles of hydrochloric acid are going to be equal to 2 times the moles of calcium carbonate. Which is 0.026. We can now work out the concentration of the hydrochloric acid by doing moles divided by volume times 1,000 . And that gives us a concentration of 1.04 moles per decimetre cubed. In this question, we've got to find out what volume of hydrochloric acid, and we've got the concentration for the hydrochloric acid, would be required to dissolve 2.3 grams of calcium carbonate. So it's very similar to the previous question. This is where we're going to have to start because we've got a mass and we've got the formula. So we can do moles of calcium carbonate is equal to mass over MR. So it's 2.3 divided by 100.1, which is 0.023. It's a 1 to 2 ratio. So the moles of HCl are going to be equal to 2 times the moles of calcium carbonate. Once we've got the moles, we can then work out the concentration. Sorry, the volume in this case, we've been given the concentration. And that's going to be moles divided by concentration times 1,000. Which gives us a volume of 459.5 centimetres cubed. At 2.05 grams of the carbonate of an unknown alkali metal. So we don't know what this metal is, but we know we're starting with 2.05 grams of it. And we know it's going to require 8.9 centimetres cubed of a 2 molar solution to dissolve it. So we don't know anything about this, even though we've got a formula. we've got an unknown in that formula, so we can't start by working out the moles. We have got enough information here to work out the moles of acid. And from the equation, we know that 1 mole of our unknown alkali metal reacts with 2 moles of acid. So we can work out the moles of X2CO3 are going to be equal to the moles of HCl divided by 2. We can then work out the MR of our unknown by doing mass divided by the moles, because the mass is given to us in the question. Okay, so that's the mass of all of this. We want to be able to take away the carbonate bit, so it just leaves us with X2. So we're going to be looking at 230 minus the carbonate is going to be the mass of X2. So X2 works out as 170.4. So X must be 85.2. If you look on the periodic table, the element that has a mass closest to 85.2 is rubidium, which is the correct classification for the element yttrium. Yttrium, if you have a look, is in the central block of the periodic table, which is the D block. This next question is looking about the trends in atomic radius across period 3 in the periodic table. So A says radius increases because the atoms have more electrons. That's untrue because the electrons are going into the same shell, so there's no additional electron shells, so in fact the radius decreases. So B, the radius decreases because nuclear charge increases. Well, the effect of nuclear charge increasing is going to pull everything in. So that one should be true, but let's just check the others to make sure. C, radius increases because shielding increases. Well, shielding doesn't increase, so that one's wrong. Radius decreases because shielding decreases. The shielding stays the same, so that one's also wrong, which must mean B is definitely the correct answer. To work out the uncertainty, or the percentage uncertainty, what we want to do is we want to take the uncertainty in the equipment, divide it by the quantity measured, and as it's a percentage, times it by 100. In this case, we don't know what the quantity measured is, but we know what the uncertainty is, and we want the percentage error to be less than 0.2. So we know that 0.2 is going to be equal to 5 divided by an unknown times 1,000. Sorry, times 100. That gives me an answer of 2,500, which initially doesn't seem to match any of these until you think about the units. This is in centimetres cubed, so this is in centimetres cubed, and our answers are in decimeters cubed. So to convert centimetres cubed to decimeters cubed, divide by 1,000, and that gives us an answer of 2.5 decimeters cubed, which is C. So for this question, you need to know the formulae of common ions. We've got a sulfate ion here, and you need to know that the sulfate ion has a 2- charge. So that must mean that Q has a 2 plus charge. So we're looking for an element that's electron configuration has 2 electrons in the outer shell, because it's going to lose those easily to form a 2 plus ion. This one is the obvious example, so the answer must be B. Okay, this question required you to think back to GCSE or possibly look some things up about the reactivity of group 7. Now basically, the higher up the group it is, the more reactive it is, and the more likely it is to be the negative ion. So, chlorine will displace iodine from sodium iodide. That one will happen. Bromine is less reactive than chlorine, so bromine cannot displace the chloride ion from sodium chloride. That one won't happen. Sodium chloride will dissolve in water just to form the ions, but it doesn't make hydrogen chloride and sodium hydroxide. And those two acids will react together. Again, this is one that you probably will have had to look up. They don't react in that way. So the answer is going to be A as the one that happens. For this next one, we have 0.01 moles of ammonia. So to find out how many molecules of ammonia we have in 0.01 moles, it's going to be 0.01 times Avogadro's number. And that gives me 6.022 times 10 to the 21. However, the question says how many atoms have we got? Well, here we've got 4 atoms. So if we've got that amount of molecules, we have got 4 times as many atoms, which is 2.41 times 10 to the 22, which is answer D. Okay, quite a little bit of work needed for this last one. So the first thing to do is aluminium chloride. We know aluminium forms a 3 plus ion, so the formula must be AlCl3. We can work out how many ions we have by first working out the moles. Now to work out how many ions we've got, we would then need to times that by 3 and times it by Avogadro's number. But as we'd have to times them all by Avogadro's number, I'm just going to times it by 3. Now I need to do exactly the same for the other ones. So we've got calcium chloride, we've got hydrochloric acid, and we've got sodium chloride. So if we do the same calculation for each one, and then we can see which one has the most ions. So you can see the one that has the most moles and therefore is going to have the most ions is this one. So the answer is B. Bromine exists as 2 isotopes, 79 bromine and 81 bromine, which are found in almost equal abundance. Which of the statements is correct? The first ionisation energy of 79 bromine is less than the first ionisation energy of 81 bromine. That's going to be incorrect. They've both got the same electron configuration, therefore they're both going to have the same first ionisation energy. Also, the number of protons does not change in either. The atomic radius of 79 bromine is less than the atomic radius of 81 bromine. Again, the atomic radius will be exactly the same because the number of protons and electrons in both isotopes is identical. The mass spectrum of this molecule here will have 2 molecular ion peaks. Now, if you work out the MR of this particular molecule, for one of them you put bromine in as 79 and for the other one you put it in as 81, you will find you get 2 masses of those two. So you would expect 2 peaks in the mass spec. So that one should be the one that's right, but let's just check the bottom one. 79 bromine is more reactive than 81 bromine. Well, they've both got the same electron configuration, so the reactivity will be identical. So that one's wrong. So again with this one, it's an uncertainty one, so we want to take the uncertainty in the equipment, which is 0.001, divide it by the mass we weighed, which is 0.250, and then times it by 100. And the answer is 0.4%. If we have a look at the answers, that corresponds to B. A student is provided with a 5 centimetre cube sample of 1 times 10 to the minus 2 molar hydrochloric acid solution. The student is asked to devise a method to prepare a hydrochloric acid solution with a concentration of 5 times 10 to the minus 4 mole per decimetre cubed by diluting the sample with water. We need to work out what volume of water should be added. So for this question, we want to work out how many moles we've got in the original sample. So my moles of HCl are going to be 5 times 1 times 10 to the minus 2 divided by 1,000, which is 5 times 10 to the minus 5. Now I need to find out the total volume of the solution I need to make up this new concentration. So I'm going to take the moles I've just worked out. This is the concentration I want. And it's still times 1,000. So that gives me a total volume of 100 centimetres cubed. But I already started out with 5 centimetres cubed, so the volume of water I need to add is going to be my total volume that I want minus what's already there, which means I need to add 95 centimetres cubed, which corresponds to answer B.